Welcome students. Now we are going to see the very important operation in the sheet metal operation. Of course, this is the forming operation, but we have taken it into the sheet metal operation or sheet metal working, that is the deep drawing operation. We are going to start with the deep drawing. Okay, so what is this deep drawing actually? So it is nothing but the process in which you are making the cup shaped components or the shell like component or shell like articles. It is nothing but the deep drawing operation. It is going to use the sheet that is blank and punch and die combination to produce these cup shapes or the shells or the shell like article. So this is, say, the given blank is available with us, okay, with the thickness T and diameter of the blank, say, D. Okay, so this blank we are going to deform into the die, so to get the cup or shell like article. Okay, so like this, suppose we have deformed like up to this, so you got here. Of course you are going to use the punch and die combination, so this is punch and say this is the die. Okay, so here we are going to produce a cup or a shell of diameter D and height H and height H. So simply you can see observe here, you are going to cup like this, you are going to get cup or shell like article. Okay, of course this is the corner radius small r, this is the diameter that you are going to produce, and this is the height of the cup. Okay, so corner radius is, of course, you have to put there to avoid the cracks or failure at the corners because of stress concentration. Okay, so this is the cup of diameter D, say sheet thickness is T in millimeter. Okay, so this is the deep drawing operation. We are going to produce a cup. Now whenever, see here, in the deep drawing operation, the height of the cup is more than the half of the diameter of cup. Okay, that is, this H will be greater than this D by 2. When this H is greater than this D by 2, it is known as the deep drawing operation. It is known as the deep drawing operation. And when the obtained height of the cup is actually less than or equal to, say, the half of the diameter, it is called it as the shallow drawing operation. Okay, it is shallow drawing operation. So we are talking about the deep drawing, so definitely there will be what, this H by D ratio will be more than half, that is height of the cup will be more than the half of the diameter of the cup. Okay, so this is the deep drawing operation. Now this is not the cutting operation. Please remember, even we talk about the sheet metal, the shearing is going to happen there, but here in deep drawing operation we are not going to cut the material. So shearing is definitely not there. So what is there? So there will be what, the deformation, isn't it? So the stress induced in this material in the deep drawing operation is greater than the yield strength of the material but less than the ultimate strength of the material. Please remember, so here we are getting the deformation, not the cutting action, isn't it? So whatever the stresses induced are greater than the yield strength of the material but less than the ultimate strength of the material. Now the very important thing in this deep drawing operation for the designers is that to determine the size of the blank that is going to require to produce the required height and diameter of the cup. So here the blank size calculation, blank size calculation is very important thing that can be done by mathematically, graphically, okay, by using the volume, by using the surface area, we can able to find out the blank size required to make the cup of diameter say small d and height h. So if I say that the blank which I have taken for the operation is of thickness t and the diameter of say d, okay, so d is the blank diameter and t is what, the thickness of this blank. So from this blank what we are going to produce, we are going to produce this cup of say diameter d and height h. Okay, now for that what we can do that, so we can do one thing. If you consider the surface area, there are various techniques to get this blank size by volume, by graphical method, okay, so many methods, but here we are using this surface area method so that I can have the one side surface area of blank is equal to one side surface area of product, and our product is what, we are going to get cup, of course the surface area of the cup, one side. So if you look at from the one side, of course it is nothing but the cross section of the blank. It looks like a circle only, isn't it? So pi by 4 capital D square. So D is our diameter of the blank, and this is very important thing, that the thing we are going to find out, the blank diameter, okay. So pi by 4 d square is equal to one side surface area of the cup. See, one side surface area of the cup, what you are getting here, you are getting this surface of the say cylinder, and here at the base you are getting the circular cross section, isn't it? So if you look from the top, what you will get here, this is at the base, this is the circle and this is the face, pi dh, isn't it? So if I write here pi by 4 small d square plus pi dh is the one side surface area of cup, isn't it? So very nicely we can get the value for d, pi get cancelled, 4 get cancels here, get multiplied this side. So d square, what you will get here, this small d square plus 4 times small d into small h. So what is the d? It is nothing but under root of d square plus 4 times dh, isn't it? So this is the formula for the blank diameter, isn't it? This is the blank size. This is the blank size that we are interested in. Very important, many times question asked, many times. So please remember the formula for blank size diameter is equal to root of d square plus 4 dh. Now see here, when we have to see the d by r ratio, okay, so here we have to see first of all d by r ratio. So d by r ratio, what, this is our diameter d and this is the corner radius r, okay. When this d by r is greater than 20, so this is the formula, okay. When to use this formula? When the d by r ratio for the given cup is greater than 20. Now when this d by r is ranging from 15 to 20, then what we have to do? We have to minus the half of the radius, corner radius from the obtained blank size, this is your the correct answer when the D by R ratio ranging from 15 to 20. So let's say the diameter is 40 millimeter and this R is say 0.4 millimeter. So of course here you will check first D by R ratio. If it is more than 20, you will simply use this much formula. If D by R ratio ranging from 15 to 20, you will minus the half of the corner radius from this, you will get the correct value. Now when this D by R is from 10 to 15, then what you will do, you will minus the corner radius from this D square plus 4dh. Please remember what you will do directly, you will minus the corner radius, you will get the correct answer. Now what will happen if the D by R ratio is less than 10? So in that case you can simply go for total surface area of the product and total surface of area of the blank. You equate that and go for calculation of the size. So if D by R less than 10, what you will do, you will go for total surface area. Here we have taken only one side surface area, isn't it? Then you will get the total surface area of the blank is equal to total surface area of the product or the cup. You will able to find out the value for D. Please remember these three conditions: D by R greater than 20, D by R in the range of 15 to 20, and D by R is the range of 10 to 15. Okay, so this formula is very important. This formula, blank size. Okay, let us take some standard cases for that. Let us say my cup is having the flange. My cup is having the flange. Okay. And this is say D2 and this is the cup height. Okay, so there is a flange for the cup, right, like this. So this is the flange now. Okay, so this is the flange you are having to the cup. So for this cup, calculate the blank size. So we know that one side surface area of the blank is equal to one side surface area of the cup. So one side surface area of blank always the available like this. Okay, with this diameter D and thickness T. Now tell me one side surface area of the blank pi by 4 D square is equal to one side surface area of the cup, that is pi D1H plus नीचे क्या होगा, this is circular pi by 4 D1 square plus ऊपर से कैसा दिखेगा, it will look like this. Okay, so of course you can use the same thing. This is the D1 by R. You check the D1 by R greater than 20. Then use the formula as it is. It is in the range of 10 to 15 to 20 minus R by 2. If it is 10 to 15, then minus R you can have like that. Okay, so this is for this standard case number 1, that is cup with flange. कैसा कप था जिसको flange थी. Okay, so this was the flange. Now let us take the second case. Say this is the cup like this shape. Okay, so whether there is a slant height or directly simply height is given. This is H. Okay, this is D1 and this is D2. V-shaped cup. Okay, V-shaped cup is going to analyze here for the blank size calculation. Okay, so sometimes see this either H or sometimes this angle is given to you, this angle theta or this angle theta. Okay, so you can get the value for the h here. Okay, so it is not like that there should be the necessity of the h this or this h. So whatever the height is given to you, okay, you can take the height there. Okay, no any issues. If slant height is given, take it as slant height. If angle is given, calculate the height. Okay, you will have no any issue for that. Actually, you can take any. So here, what is the blank size? One side surface area of blank is pi by 4 d square. For this, at the bottom it is circular. Okay, so pi by 4 d1 square plus here pi d average into h. Pi d average into h. Please remember this. So here this pi by 4 d1 square plus pi times d average is what? This d1 plus d2 divided by 2 into h. This is a slant height or this height. Any height you can directly take. Okay, no any issue. So this is pi by 4 d square. Pi get cancelled, 4 comes here. So it will be d square is equal to d1 square plus 2 times 4 comes here, this 4 by 2 is 2 times d1 plus d2 into h. So what is d? Is equal to root of, say, d1 square plus 2 times d1 plus d2 into h. So this is the diameter of the blank for producing this V-shaped cup. Okay. Again, if corner radius given, then only you can go for the consideration that I already told you. Okay. If not, no issue. Now say take the third case after this V-shaped cup, that is we are having the cup having the hemisphere at the bottom or the spherical shape at the bottom. Okay. So say this is the height h. This is nothing but say r, which is equal to d by 2. Okay, for this shaped cup, if you want to find out the blank size, how will you find out? The one side surface area of the blank, pi by 4 d square is equal to 1 is pi dh, pi d h plus at the sphere, that is half spherical. So what is half spherical surface area? That is 2 times or 4 pi r square divided by 2. Okay, so this is nothing but pi dh plus 2 pi, this r can be written as d square by r is d by 2, that is 4. So you'll get pi dh plus pi d square by 2, that is equal to pi by 4 d square. So see, pi get cancelled, so d square is equal to 4 dh plus 2 d square. So d is equal to under root of 2 d square plus 4 dh. Okay, for here no need of having this d by r ratio, as this is a radius there, spherical shape is there, so no need of any corner radius. So what is the blank size you are getting in case of the spherical bottom of the cup, as d is equal to under root of 2d square plus 4d into h. Okay, now if I take the fourth case as the hemispherical cup is there, okay, say of radius r, or you can have the diameter d. Okay, so how can you calculate the blank size for the given cup? So please try. One side surface area of the blank from where is going to produce pi by 4 d square, that is common. It is nothing but one side surface area of the sphere is what? That is 4 pi r square divided by 2. That is 2 pi r square divided by 2 pi r square, isn't it? Is equal to pi by 4 d square. Pi get cancelled. So d square is equal to 8. 4 into 2s are 8 r square, isn't it? So d is equal to under root of 8 r. D is equal to under root of 8 r. So root 8, how can you write? This 4 multiplied by 2 into r, which is equal to 2 root 2 times r. That is the size of the blank for this size of the blank for producing this hemispherical cup. Is it equal to 2 root r, or in terms of diameter 2r is equal to nothing but what? The d, say d is what? The diameter of this hemisphere. So it is nothing but capital D is equal to root 2 times 2r is nothing but simply you can write the d. So these are the special cases. For that we can able to calculate the blank sizes. Okay, you can try it at home. Let us take this fifth number as this is flange D2, this is H2, and this is as H1. Okay, so let us assume that this is the semicircle part here, not hemispherical, it's a circular, and you want to find out, and this is also provided with the flange at the top portion. Okay, so calculate the blank size for this shape. So you can take the shape. Just what you have to do, you have to equate the one side surface area of the blank with the one side surface area of the product or cup. Okay, so this is very important thing in the deep drawing operation, that is the blank size calculation. Okay, many times they are asking the question on this blank size calculation. Okay, now students, let us find out the load in the deep drawing operation. The load or force calculation, the load calculation or force calculation in deep drawing operation. So students, basically in deep drawing operation we are using the punch and die combination for doing this operation. At the same time, if you talk about the clearance between this punch and die, so of course here no cutting, no shearing is going to happen. So we are providing the clearance as equal to the thickness of the sheet. Okay, so this is the clear about the clearance. Now if you talk about the loads in the deep drawing operation, see, it is always better to do this deep drawing operation in the number of stages. It is number of stages are preferred for doing the entire operation. Why it is so? So suppose if you are going for only a single pass deep drawing operation, so the stresses induced in this operation are, if you talk about the average stresses induced, are just equal to the ultimate strength of the material, and there are very damn chances that definitely at certain critical sections the cracking or failure will occur. So that is the reason why we are always trying to have the deep drawing operation into the number of stages, or that stages are also called it as the draws or the strokes or the blows. You can use any word: stroke, blow, draw, step, pass, any word you can use. So see, suppose this is the original blank that we are having with the diameter d, and this blank is undergoing the deformation to form a cup. We know very well. So suppose this blank diameter say 120 millimeter, okay, and from that suppose I need to produce, suppose I am going to produce the cup of say diameter say 40 mm, okay, whatever the height, okay. But directly see, I am not going to have directly this 120 millimeter size of blank getting converted into the 40 mm cup diameter, okay. So how I can go for that? So I will have the number of passes for that. So say first pass I will go for this much reduction in the diameter, and at the first draw my diameter say d1, and the height which achieved is h1. Now again I will have the subsequent reductions, like now again I am going to have the reduction in diameter and increase in height. So this is say diameter d2, and the height in this draw or pass is h2. So every time what I am checking, so obtained diameter should be what? Less than equal to required one. Once it get this equal to the required diameter, so I will stop the reduction, isn't it? So like that, in number of stages, say this is pass 1, this is pass 2, again in pass 3 I got the required height or the diameter less than or equal to the required one. Say at the third stage I got the required height h and the required diameter for the cup. So like that we are going to have the number of passes. So the force is also going to be calculated in the number of stages. But let us say how to calculate this force for this deep drawing operation. So it is simple, the cross sectional area multiplied by the yield strength of the material, we can going to get the force which is indicated by P in the deep drawing operation as it is pi dt into sigma y into bracket d capital D upon small d minus C times Newton, okay. So here this d small d is diameter that you want for that cup, okay. Suppose this is a cup, I want this diameter d and height h from a given blank, okay. So d is this diameter, small d is this diameter that is required, capital D is our blank size. You know how to calculate this blank size? General equation under root d square plus 4 dh, isn't it? So this is how we can able to write the load formula for this deep drawing operation, where T is what? This thickness of the sheet, and sigma y is what? The yield strength. Please remember this is the yield strength of the material. And what is C? This is the constant to cover the friction and bending of the sheet, okay. So generally it is equal to 0.6 to 0.7, okay. Suppose it is not given in the question, you directly neglect it, so what you are remaining with? So if C is neglected, so you can have only here that P is equal to pi into D into T into sigma y into capital D divided by small d, okay. Now from this d get cancelled, so P is equal to pi dt sigma y times Newton, okay. So this is the force in the deep drawing operation. Now what we discussed? We discussed that हम कभी भी ये एट सिंगल स्ट्रोक में काम नहीं करेंगे. सो गो फॉर द स्टेज वाइज ऑपरेशन. सो also the force will be the stage wise, isn't it? So let us say I want the number of stages, I want to do the operation in the number of strokes. So definitely for the first stroke, suppose for the first pass or stroke, what will be the force? So I can write, say P is replaced by, now P1 is equal to, I will write the full formula, that is pi d, that first draw का diameter d1 into t into sigma y into bracket this blank size, initially तो यही अपने हाथ में है, divided by first stage का diameter d1. I am not considering C, it is neglected. So the force or load in the first stage is how much? This d1 get cancels, you got here pi capital D t into sigma y. Like that, if you want to find out the force or load in the second stage or second pass, how to write? This pi, मिलने वाला डायमीटर कौन सा है? सेकेंड स्टेज का d2 t टाइम सिग्मा y. नाउ which diameter you are drawing? Now capital D is no more, you are available with the first stage diameter, और इसको ही आप क्या करने वाले हो? आगे जाके डिफॉर्म करने वाले हो. सो दिस इज d1 डिवाइडेड बाय, आगे जाके मिलेगा सेकेंड स्टेज का d2. सो d2 गेट कैंसल, यू लेफ्ट विथ पाई d1t सिग्मा y, isn't it? Like that. P3, हाँ बोलो क्या आएगा? पाई, सो यहाँ पे d1 आया, यहाँ पे क्या आएगा? पाई d2t टाइम्स सिग्मा. Like that you can go on calculating the force for every stroke, every stage in the deep drawing operation. Please remember this. Once you are calculating the force, then the work done calculation is much easier. How to calculate the work done? So you know work done is what? The force into distance. So if I ask you to find out the work done at the first stage or first stroke, first pass, कैसे करोगे? So it is force into distance. So पहले ड्रॉ का फोर्स कितना है? P1 into पहले ड्रॉ की हाइट कितनी मिली? H1. So P1 into H1, you get this work done in the first stage, Newton meter. Please remember. If I ask you to calculate the work done in second stage और second stroke, क्या आएगा? Now second stroke में गया, ये diameter किस में convert हो गया? D2 में, isn't it? Diameter will be D2 now and height will be H2. So tell me what is the force? P2 into work done is equal to force into distance. So distance how much? This H2 minus H1. H2 minus H1. Like that, for the third stage we are having P3 into H3 minus H2. So you can go on calculating the work done also in number of stages. Okay, so what we see here in deep drawing operation, force calculation and work done calculation. Okay, so dear students, after talking about the force or load in the deep drawing operation, so basically this blank holding force is depend upon the tendency of the sheet or plate to get lifted. Okay, so when the force is applied by the punch on the sheet, what happened? The sheet is trying to lift in the upward direction. So this is the sheet, say, and this is our die. When the force is applied by this punch, what is going to happen? This sheet is going to lift in upward direction. Okay, and this will leads to the wrinkling tendency. Wrinkling tendency. Actually, what is wrinkling actually? So wrinkling is nothing but the foldings produced on the flange portion of the cup, like this. So your cup will look like this. Okay, so this is actually a wrinkle. So the foldings on the flange portion of the cup, this is the actually wrinkling. So these are the wrinkles, and this tendency is wrinkling tendency. So because of that, see, the calculation of this blank holding force is very difficult, and to get this value, the trial and error method is used, and empirically we are taking this value of blank holding force as the 1/3 of BHF, that is blank holding force, is equal to 1/3 of the load in the deep drawing operation. Please remember. And now of course BHF will be the same as that of the load, that is in stage, every stage it will be the different. So for the stage 1 BHF2 will be 1/3 of P2. Like that you are having the blank holding force for the every stage. And how much it is? It is generally 1/3 of this P. Now to avoid this lifting of this plate or sheet, what we are using, this blank holding force, that is these are the spring loaded plates we are going to put here. These are the strippers. Okay, so these are applying this force onto the plate so that the lifting can be avoided. So by using the spring loaded stripper, these are what? The spring loaded stripper. If get maximum, what will happen? Why it is 1/3 of only the load in the deep drawing operation? So definitely if you apply the maximum blank holding force, so what will happen? The thinning of the sheet may get happen. Okay, what happened? The thinning of sheet or blank, that is going to happen, and if it is more, so it can lead to the failure or fracture. Okay, so that is the reason why we are keeping this blank holding force actually in the limit, that is we are providing only 1/3 of the load in the deep drawing operation, and the sheet is going to fail. Okay, so this is the blank holding force. Now let us consider the stress in the deep drawing operation, the stress or stress induced, the stress induced in deep drawing operation. So now we have calculated the force. Okay, now how to calculate the stress? And of course the stress is also in every stroke we can able to calculate. Okay, so let us say we are having our cup is forming here by the force from this punch, and you know that in the deep drawing operation, how much the clearance between the punch and die? It is equal to what? The thickness. Okay, it is equal to thickness of the sheet. This is nothing but the clearance. Okay, so once if you see from the top, here, so how it will look like? This is the punch diameter, isn't it? Say this is the outer diameter, that is nothing but including the thickness. So here is thickness T, here is thickness T. Okay, if D is, we are taking D like this only, so D is the diameter and this is the height of the curve that is going to produce in this die. So tell me this distance, inner diameter will be this D, total D में से यहाँ से T गया, यहाँ से T गया, D minus 2T, isn't it? And outer diameter is D, you know that. Okay, so outer diameter here is equal to capital small d, and inner diameter will be D minus 2T. Okay, now if you want to find out the stress induced in the first pass or first stage So say sigma 1 is the stress induced in the first stage. So sigma is equal to what? P1 divided by the area in the first stage, isn't it? So P1, we know how to calculate pi d t into sigma y, isn't it? That is sigma 1 is equal to P1 divided by what is area? Which area you are getting here? That is pi by 4 d1 square, because we are talking about the first stage, minus inside area this d1 minus 2t whole square. Sorry, d1 minus 2t whole square. So you get this stress in Newton per mm square for the first case, isn't it? And one very important thing is that when the deformation is going to happen, when the sigma 1 is greater than the yield strength of the material, and of course the less than the ultimate strength of the material. Please remember, you know this, because deep drawing is the deformation process. There because of deformation the size and shape is going to obtain, isn't it? So like that you can have the sigma 2 now. This is P2 divided by pi by 4 into d2 square minus d2 minus 2t whole square. Like that you will get again the stress in the second stage. Like that you can go on calculating the stress in the respective stage or stroke very easily. Okay, so this is the stress calculation or induced stress calculation in the deep drawing operation. Okay, now in this stress analysis, okay, what I'm going to have here, suppose we have the partially drawn cup. Okay, we have the partially drawn cup, partially drawn means प्रोसेस अभी चल रहा है. ओके, एंड आई वांट टू हैव और आई वांट द stresses induced in a partially drawn cup. Okay, so let us see this. For that, what I have to draw here, the partially drawn cup. Okay, we will draw it. Say this is the die and this is the flange portion on which our blank is rested now, and it is partially, that's why I will show like this, that operation is in process and it is applying force P. Okay, so I hope it is clear now. This is the die. So this is zone number 1, and for deformation actually say this is zone number 2. And the flange portion is as, say this is second zone and this is the third zone. Okay, so first zone I will write zone number 1, that is bottom of the punch, bottom of the punch. Zone number 2, that is the deformation zone, and zone 3 at the flange portion, So what we are going to see is that the stresses induced in these 3 zones in the partially drawn cup. Okay, and very importantly, by considering the 2 conditions or cases, one is with BHF and without BHF, second is without BHF. So this is the condition. Okay, so for these 2 conditions we are going to see in each zone what kind of stresses are going to induce in the partially drawn cup. Okay, very important. Many times this question are framed on this subtopic stresses induced in partially drawn cup. So see here, let us see, we have the first zone. कौन सा zone है? Bottom of the punch. bottom of the punch. So pure tensile actually in the deformation zone. Please remember, very important. So second zone में BHF apply करो या ना करो, there will be always pure tensile is going to produce pure tensile stress. Now come to the flange portion. When you are not having at flange portion, when you are having the BHF, what the material is going to have deformation, okay, because of the tensile stress, isn't it? So only tensile with the BHF, tensile stress only. But without BHF, what will going to happen? There is a flow of material radially. Okay, there is a flow of material radially, and they are going to produce the foldings. They are going to produce the wrinkles, isn't it? So, if you look the kind of stresses that are going to induce at this third zone, that is the flange portion. So, these are two directional tensile. And compressive in third direction. Please remember. So with BHF only the tensile stresses are going to generate in the flange portion as material is flowing inside the die. But if you are not using any BHF, it will be simply lifted. Towards two directional tensile and compressive in third directional. Two directional tensile stress and compressive in third direction. So these are the stresses, kinds of stresses which are going to produce in the partially deformed cup in various zones. For example, bottom of the punch, in the deformation zone, and in the flange portion. Okay, so this is about the stresses. Now in this video we are going to see the number of draws, okay, the number of passes, the calculation for this. So many times I use this word, the pass, draw, blow, stroke, okay, the read the draws. Okay, so how to calculate this actually? So let us see the number of draws, okay, in deep drawing operation. So for calculating this number of draws, there are two techniques. So technique number one or method number one we can have, that is draw ratio method. Very easy. What is draw ratio method? So this draw ratio is equal to the diameter before drawing divided by diameter after drawing. Okay, so let us say if I want the draw ratio 1, so for that, when we are starting the operation, अपने पास क्या था? अपने पास blank size है, अपने पास blank है. For using that blank, we are going to produce the cup. Okay, so we are having before operation or before drawing क्या अपने पास? Capital D is the blank diameter divided by after drawing क्या मिलने वाला है? Cup diameter, isn't it? So simply the ratio of diameter before drawing divided by diameter after drawing. So definitely here D will be replaced by D1 because this is the first draw. Okay, now this draw ratio actually ranging from 1.6 to 2.3. Please remember. Okay, so these are the limiting draw ratios. These are what? LDR, that is limiting draw ratio. कहाँ से कहाँ तक है? 1.6 to 2.3. Okay, if in the question they are asking for the calculation of number of draws and they have not mentioned anything about this draw ratio or limiting draw ratio, you just simply consider that draw ratio is equal to 2. Please remember this, very important. Whenever no any data given for this draw ratio, you can take it as 2. Okay. So like that, you are gone calculating the number of draws to get the required size of cup. Okay, say the diameter you get from this first draw, that is D1, is equal to D by draw ratio, isn't it? Okay, so draw ratio 1, but still it is greater than the required diameter, required cup diameter, isn't it? Required cup diameter. So again, what you will do, you will go for the next draw, you will go for subsequent draw, then you will get this D2 is equal to, say, D1 divided by the draw ratio. If same draw ratio we are going to use in the every stage, then this dr will be same for everywhere. If again you are changing the draw ratios also in particular stages, then you can have this dr2 here. Again, if this is greater than the required diameter, you again go for the third draw. Okay, that is d2 divided by draw ratio at the third stage. And once it is less than equal to the required, you will going to stop there, and there will be how many stages? 1, 2, 3. So the operation, deep drawing operation, can be done in these 3 stages. Okay, like that we can able to find out the number of draws. Let us I will take one example. Say, suppose a cup of diameter 15 mm is required, and height of the cup we required as 60 millimeter. Okay, and the question is, calculate the number of draws required to do this drawing operation. So here, first of all, we required what? The blank size, very important. Blank size is very simple, under root d square plus 4dh, isn't it? So diameter kitna hai cup ka? 15 square plus 4 times 15 times 60. So how much it is? If we solve it, 60 square plus 225 under root, answer. So it is around 61.84. 61.84 millimeter. Okay, so this is the available blank size with you, and this blank size you are going to draw into the required cup diameter and height. Okay, so here nothing is mentioned about draw ratio, isn't it? Nothing is mentioned about draw ratio, so simply we can take it as draw ratio. How much you are going to take? It is 2, isn't it? So let us write the draw ratio is equal to what? The diameter before drawing it was d divided by d1 we are going to see. So d1 will be what? 61.84 divided by, what is draw ratio? 2, isn't it? So d1 will be what? Divided by 2. 61.84 divided by 2, that is 30.92. आपने को चाहिए कितना? 15 मिलीमीटर. पहले स्टेज में मिला कितना? 30.9. So which is greater than 15. So again you have to go for the second pass. So second pass में क्या मिलेगा? This 30.92 divided by 2. Okay, so how much it is? Divided by 2, it is 15.46. 15.46, which is again greater than 50. So definitely in the third stage, how much you will get? You will get 15.46 divided by 2, that is 7.73, which is less than equal to 15. Okay, that is the capability of the third draw is to take the diameter to the 7.73 millimeter. So, but of course in the second draw it is greater than 15. So definitely we have to go for the third draw. It is not like that कि direct 7.73 पे जाके रुकेगा. It is not like that. We can control the diameter. Once you get this 15, you can stop the operation there. Okay, and required 15 mm only you can get. It is not like that the cup will directly go to 7.73 millimeter. It is not like that. Please remember. So of course at the third stage the diameter now lesser than equal to 15. So how many stages you required, or how many draws required? Question was same only, na? Calculate the number of draws. Say draw number 1, this is second, and in the third draw the operation get complete, you reach to the 15 mm diameter. So the answer is 3 draws. Kitne draw lage? 3 draw lage. Like that you have to solve the questions. Now the another technique to calculate the number of draw is ratio technique, draw reduction ratio technique or method, that is known as a DRR. So how to calculate DRR? So DRR is equal to, so D minus D divided by capital D into 100. Okay, so the initial diameter minus the diameter in the respective stage divided by initial or original diameter, you will get the draw ratio. Very simple. This is percentage reduction like thing. Okay, so if I want to write for DRR1, okay, DRR से पहले draw reduction ratio के लिए, then it will be D minus D1 divided by D, that is D is the blank size and D1 is the diameter in the first stage that I am going to get. Okay, into 100. So it is in percentage. So draw reduction ratio in the first stage is about 45 to 50%. Please remember this. Okay, so definitely draw ratio पहले स्टेज में अपने को कितना मिल सकता है? 45 to 50%. That is draw reduction ratio we are getting here. So suppose directly from the given data, suppose you have got the value as capital small d, that is required diameter, divided by blank diameter. If this ratio is more than say 50%, so definitely you have to go for this reduction technique in the number of stages. Okay, so for first reduction you got is about 45 to 50%. Like that you are having the draw reduction ratio in the second draw as now available diameter D1 minus going to get the diameter D2 divided by D1 into 100. Okay, like here 30 to 35% of reduction you are going to get in second draw. And now see, when you are going for the third or fourth draw, it is very important to have you remove the material and go for the enhancement of the ductility by the annealing operation. Okay, so that you can get the further deformation, further reduction into the deep drawing operation. So third draw, it is D2 minus D3 divided by D2 into 100. Around 20 to 25% of reduction you are going to get here. And last DRR 4 and above, 4 या उसके ऊपर, so maximum reduction you can get D3 minus D4 divided by D3 into 100, isn't it? That will be nearly about 16%. So easily again we can have the number of draws you can able to calculate. Kitne draw if you are having the draw reduction ratio technique. So in this fashion you can calculate the number of draws. Okay, so let us discuss one example where we are going to consider this draw reduction ratio technique. Okay, so students, let us discuss this example. The question is a cup of 50 mm diameter and 75 mm height, this is the deep, okay, that is height, is to be drawn from 1.5 mm thick steel sheet of deep drawn quality of the tensile strength 300 megapascal. Neglecting the corner radius, calculate number 1 the blank size and the force and energy required for the first draw. In the reduction in first draw, how much? 40% is given. Okay, so see, diameter of cup how much? 50 millimeter. Height of the cup is 75 millimeter. Say sigma tensile strength is given, isn't it? We want here sigma y. So please remember, many times in deep drawing questions they are giving us the ultimate strength of the sheet or they are giving the tensile strength of the sheet, but we want here sigma y, yield strength of the sheet, that is generally we are taking as half of this tensile strength. Okay, so here sigma y will be 300 divided by 2, it is 150 megapascal. And then you can go for the calculation. Draw reduction ratio in the first stage is how much? 40% is given. Okay, now what is the blank size? Very easy thing. Corner radius is not given, so directly blank size is equal to under root of d square plus 4dh. So what is diameter? 50 square plus 4 times 50 times 75. What is the answer? See, you will get this answer for this D as 132.3 millimeter. So first bit of the question is clear. Very simple calculation of the blank size. Okay, so diameter of the blank, we get it here. Now what they are saying, that the first draw the reduction is 40%. So let us go for the calculation of the force and energy for the first draw. पहले draw के लिए क्या पूछा है उन्होंने? Force and energy they have asked. So let us say the force for first stage, we know it is P1 is equal to what? Pi d1t into sigma y into bracket capital D by D1 minus C is not given, then it is not there, so get 0. So D1 get cancelled, so pi times capital D times T into sigma y will be the force in the first stage. So put the values. P1 will be equal to pi into 132.3 into thickness is how much? 1.5 millimeter into yield strength 150 megapascal. So if you calculate, you get it here 93.5 this kilonewton. Okay, so this is the P1. Okay, now the force also get calculated. Now energy in the first draw, energy is how much? That is P1 into H1. Okay, now H1 is here important. So what is the height in the first draw? To calculate this height in the first draw, we know that this D is equal to under root of, now write for the first draw, D1 square plus 4 D1 H1. Isn't it? Now what is the blank size for the first draw? 132.3 is equal to, sorry, we need this diameter. Okay, to calculate the H1 we need this D1 also, isn't it? So how much first draw के लिए कितना reduction दिया है? So first draw reduction ratio for the first draw is how much? This is D minus D1 divided by T into 100. So it is given as how much? 40%, that is 0.40 is equal to capital D 132.3 minus D1 divided by 132.3. So calculate for D1, it will be how much? 132.3 into 0.40 and 132.3 minus this, answer you get 79.38. So D1 will be 79.38 millimeter. Okay, now use this D1 value in this equation. You can able to get the value for H1 that is the height of the cup in first draw. Okay, because you want to find out the energy in the first draw, that is P1 into H1. So what is value of D? 132.3 is equal to under root of D1 79.38 whole square plus 4 into 79.38 into H1. Dear students, please calculate for H1. I will write directly here. I am having this value as 32.3 millimeter. Okay, so this is H1. Now very nicely you can calculate the energy in the first draw, that is say work done or energy same, which is equal to P1 into H1. So P1 कितना था अपना, having 93.5 kilonewton, so into 10 to the power 3 Newton, into H1 32.3 millimeter. We have to convert it into meter, that is into 10 to the power minus 3. And if you calculate, you will get the answer nearly equal to 3 kilojoules. Please check and tell me. So work done or energy in the first draw कितनी मिलेगी आपको? 3 kilojoule. So this is the answer. Understood how to solve this? Please check. Dear students, in this video we are going to discuss the various or the most common defects in the deep drawing operation. So in the deep drawing operation, the one of the most common defect that we know already, that is the wrinkling. So this is the most common defect that we are observing into the deep drawing operation, where there are the foldings or the lifting of the sheet in upward direction when this force is applied by the punch on the sheet. So what happened, because of this lifting, the foldings are produced on this flange portion. Okay, so we are getting this foldings at the flange portion of the cup is nothing but the wrinkles. Okay, so this is most common. So again, this is what material is flowing the radially, so we are getting these foldings. Okay, so the main reason behind production of these wrinkles is basically the insufficient blank holding force. Okay, so we have to provide the necessary blank holding force to avoid the lifting of the edges, so that the foldings will not produce. You can able to eliminate the defect called it as wrinkling. So actually the wrinkles which are present on this flange, these are the flange wrinkles. Sometimes what happens, the wrinkles can be extended up to the wall of the cup, and say this is wall of the cup, and it is now producing the wrinkles on the wall of the cup like this. So this is our cup. Okay, so these are known as the wall wrinkles. These are nothing but, these are the flange wrinkles, and these are the wall wrinkles. Okay, so these are the wrinkling. So the main remedy for is what? We know that we have to provide the sufficient amount of blank holding force so that the lifting get avoided and these wrinkles can be eliminated. Now the another remedy to eliminate the wrinkles is that we know that in deep drawing operation, the clearance we have provided is generally equal to the thickness of the sheet. That is clear. Now, but in the deep drawing operation, this nothing but these wrinkles are caused due to the flow of the material radial direction, in the radial direction. That's why these foldings are getting produced. So actually in deep drawn curve, you see the cross section, the side walls are becoming thicker than the bottom of the sheet. Okay, So we can do, and this material is going to flow here in terms of the wrinkle it is going to generate. So what happened, to avoid this thickening of the sheet in the side walls of the cup, what we are doing is that we are providing the clearance in the deep drawing operation is slightly less than the thickness of the sheet. Okay, that's why what will be happening there, if you are keeping the clearance in the sheet, deep drawing operation less than the thickness of the sheet, then definitely what is going to happen, this material getting squeezed, isn't it, and it will flow uniformly with the pressure, so that it can go and equally distribute on the flange portion. So what happened actually, and that action or that effect is known as the ironing effect. So what is the ironing effect actually, that we want to squeeze that material from between the punch and die, so that we can able to eliminate this radial flow which is non-uniform, producing the foldings which are nothing but the wrinkles. So this effect, that is provision of this clearance, this is clearance, and we know in deep drawing it is thickness, but we are providing this clearance slightly less than the thickness of the plate. Okay, that's why the material gets squeezed in between this gap, and it can eliminate the wrinkles. Okay, so first remedy, to have the sufficient amount of blank holding force. So on the edges you can have the blank holding force by using the spring loaded strippers. Okay, and the second remedy that you have, that is the ironing effect. Okay, now the next defect in the deep drawing operation is that the ear or lobes, the ear, very important, please remember, first defect is the wrinkles or wrinkling, and the second defect that we are going to discuss is the earring, or these are simply what, the ears or lobes. Where these are going to get produced, these are producing on the vertical wall of the cup, on the wall of the cups, say these are going to produce. So these are nothing but the lobes or ears, the lobes or ears. Okay, so on the vertical wall, this is wall, you can have this ears. Now see, in the ears, you can also call it as the wrinkles which are present on the vertical wall of the cup are known as the ears. And the main reason for producing this earring effect is, see here, you can have the ear which is compressing here is subjected to the compression, whereas the outer layer which is coming out, it is subjected to the tension. It is no. So in a single plane, if you talk about this, so in a single plane we are having different properties. At inner surface of this ear, it is compression. At the outer surface of the ear, it is tension. So in a single plane, if you are observing such a kind of different properties, so definitely this property is actually nothing but what? This is nothing but the planar anisotropy of the material. Anisotropy. At a point in a directions, properties are changing, that is the planar anisotropy, and this is the reason for this production of these ears. Okay, so the ears or the lobes are going to produce because of the planar anisotropy, called it as the earring defect. Okay, now how to minimize this earring defect? Okay, so of course the production of BHF is one thing, or you can have the use of the draw beads, So this is the die. So you can use here this semi spherical depression onto the flange portion, and this is your dies get hold, and this is your punch. So these are nothing but the draw beads. The draw beads, these are the draw beads. Okay, so the radius of the draw bead, sorry, the diameter of the draw bead is actually from 30 to 20 millimeter. Please remember, diameter of the draw bead कितना रहता है, 13 to 20 millimeter. But again, see, the earring defect is cannot get eliminated completely. Even though the use of the use of the draw beads, using of the BHF, it is still present onto the, so it is not in our hand. So ultimately, whatever the ears are going to left by doing this, by provision of the BHF, by doing this provision of the draw beads, whatever the ears now left, they simply are going to cut it, and you are going to get the required dimension. But what happened, as we are going to use this trimming allowance, so you have to put the excess size, okay, so that it can be get cut to after the process, and it will give to the trimming allowance. So for that, in advance we have to provide this trimming allowance कि भाई ये ईयर्स जाने वाले नहीं है, वो उसको फाइनली कट करके निकालना है, तो हमको कुछ एक्सेस डायमेंशन देनी पड़ेगी किसके ऊपर, ऑन ब्लैंक डायमीटर. ओके, ये जो कब बनेगा, किससे बनेगा, इट विल मेक और मेड बाय दिस ब्लैंक of diameter D. Okay, and we are finally going to trim this produced diameter to account for the ears. So definitely I have to add some extra diameter onto the blank, isn't it? So at that time, if you are given with the trimming allowance, so by thumb rule, see, this is by thumb rule, it is given as 3.2 millimeter on 25 millimeter of the cup diameter. Please remember it. How it is given as 3.2 mm on 25 millimeter of cup diameter. Or if it is given radially directly, then it can be asked, if you find out the diameter of the blank by provision of the trimming allowance, that is, so D total, here I will write D total is equal to D, that is our blank size that you calculated. In that you have to add 2 times trimming allowance, like that you can add the trimming allowance. But thumb rule क्या कहता है, you have to add 3 millimeter or 3.2 millimeter for every 25 millimeter of cup diameter, and that you have to add into the capital D. Let us take example that so that you can able to understand. So say this is our cup, of say 48 millimeter diameter and 48 millimeter height. Okay, you are going to have the cup of 48 millimeter diameter and 48 millimeter height. And in the numerical, suppose I am saying that the trimming allowance is how much? Say 3 millimeter on 25 millimeter of cup diameter. So find out the D total. Okay, so this is the actual blank size that we have to take in account of the trimming allowance, isn't it? So what is D total? D total, how to provide this? So D total will be D plus, this is 3 millimeter over 25 mm for the cup diameter. Cup diameter कितना है? 48 millimeter. So for that, first of all calculate this blank sides. D is equal to what? Under root of D square plus 4DH. So diameter 48 square plus 4 times 48 diameter, and height also 48. So if I calculate, so 48 square into 4 plus 48 square, root of answer, it is around 107.33 millimeter. So what is the value of D total? So D total will be 107.33 plus this value is how much? 48 into 3 divided by 25. So it is 5.76. So what is your D total? Plus 107.33. So 113.09. 113.09 millimeter is your D total. That is, this is the theoretical blank size, but when you are accounting the years also here, that they are going to cut by provision of the trimming allowance, this will be the actual diameter that you have to put for the blank size. Okay, so this is how we can able to calculate the actual blank size by provision of the trimming allowance. Okay, now see this number of ears that are produced in the deep drawing operation. So see this, in the earring defect, the number of ears can be given as 2 to the power n. Okay, how to get the number of ears? It is given as 2 to the power n, where n is the integer which values depend upon the properties of material, friction, bending, all these conditions. So generally, please remember that. So number of ears are given as 2 to the power n. So suppose in the examination they ask you to calculate, and the options are, okay, say it is 14, option B is 25, option C is say 30, and option D is 32. Okay, so what will be the answer to calculate the number of ears if they ask? So it should be 2 to the power in terms of this. So the answer is only what? 32, isn't it? 32 should be the answer. That is 2 to the power. If I say 2 by 2 by 2 by 2, 2 2s are 4 2s are 8, 8 2s are 16, 2s are 30. That is, n here is 5. Okay, then only we will get this 32. So number of ears produced are how much? The 32. So this is the second defect, and the remedy for that we have seen. Now the third important defect in the deep drawing operation is the orange pill. The third defect is what? Orange. So this orange pill, this is kind of metallurgical defect that is going to produce in the deep drawn component, where we are get the dull surface. How you can see dull surface you are getting on the drawn cup, onto the drawn cup. It is because of what? The large grain size. This is because of large grain size. You are getting the surface which is, you can see on the orange pill, that kind of surface. This is a metallurgical defect you can get onto the drawn cup. Okay, the dull surface, which is because of the large grain size. That defect is known as the orange pill. Okay, so these are the main three defects in the deep drawing operation: wrinkling, earring, and the orange pill. Okay, so I will look into that. Thank you.